In this video, I want to show you all of the ggplot2 geom functions that you can use to visualize your data or analysis results in R. The more you know of them, the better you will be able to turn your data into charts and stories. Just to mention, I do have longer dedicated videos about some of these on my Data Digest channel. Just look for the R Graph Gallery playlist. Without further ado, let's start with the R code. If you ever want to know which functions are included in a package, you can use the ls function and then type package ggplot2 and you will see all the functions that are part of this package. And now with the grep function, you can extract the names of this package that start with the geom string and with value equals true. You will see all the 53 geom functions of the ggplot2 package, and I'm going to show you 50 because there are 3 pairs of functions that are the same version just written differently. Let's set the theme to theme light and start with the geomPoint function. There are different ways how you can use the ggplot function. You can provide a data set for the data function argument and then use the AES or the aesthetics function to map certain values on the x and y axis and then follow up with the geom, in this case geomPoint, to create a scatter plot. I prefer to do it in this way, that I pipe the data frame into the ggplot function and then just follow up with the AES. This way you can sometimes filter the data frame or perform mutates or join other data sets and only then start your visualization functions. And always make sure that everything you follow after ggplot is added with the plus sign. And now it's really easy to add color to the scatter plot by using the color function argument and pass over the species column. And within geomPoint you can increase the size, and with alpha increase the transparency. In case you are ever concerned about overplotting, you can now see where multiple responses have the same x and y values. A second way to deal with overplotting is to use the geom jitter function, which adds some noise on the x and y axis. And geom jitter also works really well in combination with the boxplot. In case you use geomPoint with a categorical variable on the x-axis like species, this is actually something you would do in combination with the geomBoxplot function. And here you could add geomPoint on top of the boxplot, but it's even better to use geom jitter because now you have a better understanding of the actual data points and their distribution. In this context, the order actually matters. If you start with boxplot and then add the point, the chart will look different than if you would first start with the points and then add the boxplot. Of course, you can always increase the transparency of the boxplot and then you would still be able to see the first added points. Also notice that sometimes the boxplot comes with outlier points, which would lead to duplication of data points, and those you can avoid by setting the outlier shape to NA within the geomBoxplot function. And now they are gone and you only see the points from geom jitter. Next, the geomViolin function is similar to the boxplot, but it gives you a better visualization of where the actual points fall in the distribution, whether it's symmetrical or skewed in one direction or another. And in case you want to put 2 charts in the same plot, you can assign the boxplot to P1 and the violin chart to P2 and then enter this code separated by a / to put them on top of each other. The next function is geom.plot, which again is similar to violin or boxplot charts. Now the main difference is that you don't use color but fill to assign a color to the dots, because color is the outline of the shape and fill is the inside color. You can also specify which bin axis you want to use to combine similar values into one distinct category. The direction of the stacking, you can center align them, and then you can provide a dot size. Now let's leave the dots behind for a while and move on to bars. Here we have the MPG dataset that comes with a class variable that lists different types of cars. And whenever you have a vector of different categories, you can use the geomBar function to visualize the sum of each individual type. So the 33 pickups, geomBar turns it into a bar like that, based on a vector of type entries. Now if you don't have a vector of types but a dataset that already gives you the results, like in this case you can pipe mpg into the count function and count all the entries of class. Now if you wanted to pipe this result from the count function into ggplot and use class on the x-axis and n on the y-axis in combination with geomBar, you would get an error message, because it actually wants to count the number of types by itself and don't use this results number. You could get it to work by using stat equals identity. Now you get your chart, or what I like to do is to use the geom call function because this function can actually work with a results table like this by default. And as I said, if you want to change the color of these bars, don't use color because this will just change the outline of the bars. You would have to use fill, and you can keep the color within geomcall as black for the outline, but map the class itself within the aesthetics function to the fill function argument to get these 7 rainbow colors. For the next 3 geoms, I will be using the diamonds dataset, which contains over 53,000 diamonds with 10 variables, like the weight in carat, the price in dollar, and then some cut, color, or clarity variables. And the first thing you can do is use the geomhistogram function to plot the price and see how many diamonds are available in these different price categories. You can set bins to 50 to get more of these buckets, use color black for the outline and light gray to fill it. Now let's zoom in to the price range of 0 to 8,000 and try to add the cut variable as a fill argument. This will turn histogram into these stacked bar charts of various diamond cuts, but now it's not really easy to compare the different levels of cut. You could use position equals dodge, and then when you zoom you could see the levels side by side for these different price ranges, but a better solution would be to use the facet rep function to put these 5 levels below each other, which immediately tells you that most of your cuts are very good, premium, or ideal with different distributions. And if you set the scales argument to free y, each distribution gets its own y-axis extending to the maximum value of each grouping. If you want to keep all the different levels in the same plot, I suggest using the geom freqpoly because it counts the number of observations for each cut level, giving a certain bin width, and then the size increases the line width. And so you could in one chart compare the different frequencies of your different cuts. The geom density function does something similar, except for now it's not counting anymore, but it's giving you the density distribution of each level, and those areas under the curve would always add up to 1, but it shows you if one cut deviates in the price distribution from the others. And speaking of distributions, here I used the geom density function one time for the petal width and one time for the sepal width. And you can see that the 3 species are easier to differentiate on the petal width variable, but for sepal, their overlap is much bigger. So that's a good way to compare distributions of your variables. Now we will move on from bars to lines, starting with the geomLine function. So here I created a data frame called line_df that holds 6 different pairs of x and y values. And what the geomLine function does is looking for the smallest x value, 1 and 2, and connecting it with the next smallest x value, that's the 2 and 3 pair, in a direct manner. And then it's looking for the shortest way to the third lowest x value, which is the pair 3 and 1, and so on. geomStep, however, is a little bit different. It still looks for increasing x values, but instead of the direct connection to the next point, it's going in a stepwise manner by first moving horizontally to the next x value and then moving up vertically to the corresponding y value, which means that from 5 and 2, it moves horizontally to the 6 and only then moves up to 3. GeomPath, on the other hand, behaves completely different because it takes into account the order of the actual data frame. So it starts at 1, 2 and now looking for the next point, which is 4, 4, and then it moves to the pair 3, 1, 5, 2, 2, 3, and then 6, 3. And I will link to Andrew Heiss's post where he recreated Napoleon's march in 1812 with the GeomPath function, indicating the different location and the army strengths on the way to Moscow and back. Just a quick example to color multiple lines in the same plot. The Gapminder dataset contains various different countries, over half a decade of information with their life expectancy, population and GDP per capita. So here I just created a subset for China, India and the United States. And if you pipe this subset into the ggplot function with year for x and life expectancy on y, and you add geomLine, you get this weird pattern because it now has multiple values for each year based on the 3 different countries. And to fix this, you have to include the group variable, so it knows now that each country is its own line. So now you get 3 lines, and you can map the color to these countries. You can also add geom_point to the lines. But now keep in mind that it doesn't have color information because the mapping was only done within the geom_line function. So if you want to change the color of the point as well, make sure to map it within geom_point. But what I prefer is to do all the mapping initially in the ggplot function and then just add the geoms. And if you also map the country to shape, you will be getting circles, triangles, and squares. And in case you wonder what happened after 1960 in China and why the life expectancy got this bump down below 45 years, you can look more into the Great Leap Forward. Next, I want to show you the geom_area function, where I created just 20 values of x and y, and geom_area is like a line where it colors the area below the line with the fill function argument. Here's another example of a stacked area chart where I created data that has time values that repeat for the 5 different groups and then different values for the y-axis, and then on the next time item you have A, B, C, D, E again with different y values, so it connects these lines and stacks the areas on top of each other. Now the geom_hline or horizontal line function can be used to just add horizontal lines to your chart, and this can be useful to indicate certain areas of your chart. In this example, I just colored the point based on whether they are above or below 70.5 and 22.5 miles per gallon, and that's where I then used the y-intercept function argument for geom_hline to add a dashed line that you can give by line type. Then you add another horizontal line, and the rest is just labeling the chart, the x, y axis and the legend. And when there is a horizontal line, there must also be a vertical line. In this case, I used vline and the x-intercept to indicate areas where the weight is between 2.6 and 3.5, which is the area where you find cars with 6 cylinders, just to make it easier in the scatter plot of mileage versus weight to find where the 6-cylinder cars are located. Now geom_hline and vline are a bit limited in a sense that they only move horizontally or vertically and just have one position argument to hand over to know where the line starts, and then it just moves all the way through the chart. Geom_segment, however, can be used to draw a line from any place to any other place in your chart. Geom_segment comes with a variety of lineAnd and lineJoin function arguments. So with the expand grid function, you can create different combinations of lineAnd and lineJoin. And then in Geom_segment, we use a lineAnd and lineJoin and also the arrow function argument. And here you can see how the end of the line would look like and also how the arrows are created and their shapes. Going back to the empty cars dataset, now coloring the cylinders again, we would be able to use Geom_segment and specify the x start and end coordinates of all the cars with 6 cylinders. And for y start and end, we just use one value, which is the average mileage for these 6-cylinder cars. So this is a nice summary line showing the range of the green dots and the center of their mileage distribution. Now geom_rect is even more convenient because rect is for rectangular and it creates not only a line but any kind of rectangle you want to produce. All it needs is xmin and xmax, ymin and ymax, and then it connects the dots into this square-like shape. You either add the dots afterwards or use a high alpha value, but you can also set fill to an A and then your square is not filled. Next, I want to show you the geom_abline function or abline, which stands for A for slope and B for intercept, because if you run a linear model predicting mileage based on weight for the empty cars dataset, you will get an intercept and a slope, indicating which line would be the best fit through these points. So we would be able to put these into the function arguments of the geom_abline, being intercept and slope. And then you get the fit through the scatter plot with this orange line. Another way to fit a line through your scatter plot would be to use the geom_smooth function, where you can specify the method as being linear model and the color again. And by default, geom_smooth will find not a linear model to go through your scatter plot, but for each area of the weight find a line that best predicts the mileage. And this gray bar is the standard error of this prediction. So if there's more data points, this error band gets smaller, and if there are fewer data points, it gets wider. If you map the cylinders to the color of the scatter plot, then GEOMS Smooth will add a separate fit to each of the 3 cylinders. You could modify it in a way to have straight lines fit through the dots by using method equals lm for linear model, and you can reduce the standard error band to a certain value or remove it completely by setting SE to false. Now imagine you have a scatter plot of your different cars and you actually want to label or add text to your dots. You can extract the row name information of empty cars, which holds the model names, and assign it to a new variable called model. And now the mapping to the label function argument happens in AES again, where you hand over the model variable to label. And now you can follow up the geom point with the geom text geom, and it centers the text of each of the different models right on the dot, causing some overlap. You can use some horizontal and vertical adjustment with these function arguments, and now they start right after the dot. The difference to geom label is that the text now comes inside its own padded box, which you could also fill with some color. And just so you have heard of it, there is an extra package called ggplot2, where you have a geom text repel and a geom label repel function, and this will automatically coordinate the labels of the text to whichever space is available, sometimes omitting a few points, but if you decrease the size, you will be able to fit more labels into your plot. The geomrug function adds these little lines whenever there's a data point on the x and y axis, creating this rug-like pattern that you might know from some carpet types, so without rug and with rug. Here the color mapping to the cylinders is carried through again, indicating which cylinder comes with which value. And just to mention one function argument for geomrug, here I set sides to B. You have top, right, bottom and left, and if you set it to B, you only have the rug pattern on the bottom, but you can include these letters to put the rugs wherever you want. The next geom is called geom curve, and it's very similar to geom segment as it connects 2 points, but you might have guessed it, instead of a straight line it now comes with a curve. So this is just a data frame for the start and end points. B is an object that holds our basic empty cars scatter plot with weight and mileage, and then to that we can add the geom curve based on this data frame, and we can add the geom segment for better comparison. Now the curvature will indicate how straight the line is. If we set it to 0, it becomes a straight line again. If you set it to 1, it becomes really bendy. And within geom curve, you also have the arrow function argument again, where you can add a little arrow at the end. Now for the last geom of the first half, I create a data frame with expand grid that just gives 100 values of these different combination of 1 to 10 for x and y. And then we add to the data frame an angle and a speed variable, and spoke look like bicycle spokes, where you can have a fixed radius value, but angle mapping the angles that were created with this runif function. So now we have different angles extending from the x and y values. And if we also map speed to the radius, these lines will become shorter or longer, and then it looks like this. So a very quick way to add lines of a certain length and angle to a variety of data points. In the next section, I want to show you 6 geoms that can be used to visualize errors or uncertainty of your results or estimates. Let's start by creating an example data frame. So now we have group, treatment, and a response that comes with an upper and a lower limit for these response values. We can start with a basic chart that does not have a geom yet, where we put treatment on the x-axis, the response on y, and color the different groups. And if you add the geom linerange function to this basic plot, where you map the y min to the lower, y max to the upper values, it will connect these range values with a simple line. Geom point range behaves very similarly, but it adds a point at the actual response value, so at 5, 1, 4, and 3, additionally to the line that connects the upper and lower boundaries. Next we have geom crossbar, which again shows the actual response as this horizontal line with a certain width that we provided, and then this box includes the upper and lower boundaries. And the geom errorbar creates this more familiar shape where the upper and lower boundaries have these horizontal lines and they're connected by a vertical line. And these error bars can be very useful if you want to indicate how certain you are about a specific data point, which usually comes with some error in your estimate. So I just created an example data frame with 3 different groups, and each group has their own x and y values with a specific standard error. So now we're able for GEOM errorbar to calculate the y max and the y min based on the actual y response, plus minus the standard error. In the original mapping, we can map the color and the shape to the group variable and then follow up with a GEOM line, GEOM point, and GEOM errorbar. 2 more examples where the GEOM errorbar could be useful in combination with another GEOM like GEOM line, here to better indicate that these are the same group that respond differently to the treatment, and here in combination with GEOM call to show what the standard error is in the estimate of this treatment response for the different groups. The GEOM errorbar function also comes with a horizontal version, GEOM errorbarh, where you now simply flip y max and y min to x max and x min, and you get your errors spreading across the x-axis, which is very similar to using the regular GEOM errorbar and then just adding coordinate flip to it to switch x and y axis. For the GEOM ribbon example, we will make use of the levels of the Lake Huron from 1875 to 1972. It's a small data set that just has the year and the level measured in feet. So we can map the year to the x-axis and the level to y and draw a simple line chart. But we can also follow up with the GEOM ribbon, where we map a y min and a y max to the actual level by simply adding or subtracting 1. So that's just for this example to indicate how a ribbon would look like. Now to make the actual line reappear, you can set alpha to a really low value or change the order, where you start with GEOM ribbon and then follow up with the GEOM line. Moving on to GEOMs that help you to summarize the spread of your data by either putting it into boxes or summarizing it by certain lines. So the GEOM density underscore 2D or simply 2D can be used to create these kind of contour lines that indicate where most of the species responses fall. For the next GEOM, we will be looking at a dataset called Faithful from a geysir that has eruptions of a certain length in minutes. And usually you have to wait a certain amount for these eruptions to happen. And with GEOM density 2D, you create these contour lines that show where most of the responses cluster, so the densities of your observations. But with density filled, you would be able to add a color dimension to this density, making it a bit more clearer compared to the simple contour lines where most of the responses happen. So the highest density would have the brightest color. Now there is a dataset called FaithfulD, which is part of the ggplot2 package, and this includes the density information along the eruptions and waiting times. And this we can use for the GEOM contour, because now we can include a z-axis for the density. And this is how the GEOM would look. You can include the bins function argument, and if you set it to 5, then the number of lines will decrease to the bins you're choosing. So now you have 1, 2, 3, 4, 5 bins. And this GEOM also comes with a filled version called GEOM contour filled, where now your 5 bins have some associated density ranges. Next we have GEOM bin that comes with underscore 2D or just 2D. Both do the same thing. So for the diamonds dataset with these 50,000 observations, we have the weight in carat and the price on the y-axis. And GEOM bin 2D creates bins on this 2-dimensional chart where the count indicator is colored, and it will tell you that these heavy and pricey diamonds are a lot rarer than the small and cheap ones. You can again increase or decrease the resolution by handing over a bins number, and now the boxes get a lot bigger. GEOM hex behaves in a similar way, but instead of squares or rectangles, it creates these hexagons with this beehive shape. And here's where you can reduce the resolution by including the bins function argument. You remember that for the geysir faithful data, we plotted eruptions versus waiting time and then created these contours filled with their density. Now GEOM raster does something similar, but very granularly for the whole area where we have data. We map the density that's included in the faithful D dataset to the fill option, which will then color each of these small squares of the so-called raster. And one cool thing you can do in GEOM raster is set the function argument interpolate to true, and this will turn the raster into a very smooth gradient. So now these small squares that has this grid appearance will turn into this smooth gradient. For the next GEOM tile, I created a tile data frame that has X and Y values indicating the position of these tiles. I have 5 different groups and then a W coordinate for the width. And if you pipe this data frame into ggplot with the appropriate mapping for X, Y, and group, you can create these tiles automatically with GEOM tile, and black is just used for the outline contours. And if you include the W variable and map it to the width of the tiles, it will automatically increase the area for the few responses that have an increased width. So it still starts at 2 but expands 2 to the left and 2 to the right, making it a width of 4, and this could be used to create some mosaic blocks or tree maps. Let us move on to the geomap function, which can be used, not surprisingly, to create maps. For example, here showing the murder rate per 100,000 in the United States. And in combination with the coord_sf function, you can turn it into a proper map visualizing the spheric nature of the globe. This leads nicely to the geomsf_label and text functions that can be used for mapping as well. So for these functions we load an object from the systems file that holds the counties of North Carolina, and then you can plot this dataset with the geom_sf to create this map. Next we create a subset for North Carolina based on specific coordinates. So this will create a data frame that looks like this with a bunch of county parameters, for example the name and the area. And when we select to plot only the first 3 rows, geomsf will turn that into a map, and then geomsf text will use the mapped label to the name with a certain color to put text into these districts. You can of course do all the aesthetics mapping within the ggplot function and then just add the geom of sf or sf label, and the difference between text and label we already covered. Label will put the text in with these nice little boxes, which you could fill with any kind of color you want, for example gray. And these geoms can also be used to show you the entire world map, even from a different angle. Next I want to show you the geom polygon function. If you remember the line data frame, it just had 6 coordinates of different points, and the geom polygon will connect the dots in the order of the data frame, and then whenever there's a shape created by the overlapping line, it will be colored in. And this again can be used to create maps by having a data frame like the map data world that comes with longitude and latitude information and grouping, so it knows which polygon creates which country. This also works for the United States, but here you have to be really careful that the group is actually not based on region or on one, because then the line connection will be all messed up, but it has to be set to the group variable. So just to give you a glimpse, this data of the states has long and lat information, and then for a specific state a repeating group number that should be used for grouping. So now you have this map of the United States, and you can turn that into a fun game of guessing the shape of the state, where you sample a random state from the list of unique states from this map, and then pull out the region or the state name and use this to filter the entire state's map. And then you can guess that this is California. Here you have Michigan. It can get really tricky. Not sure if anyone would guess this to be Colorado. And this is Idaho. You can also play this for the world map. Here I'll just give a few examples. If you set the random country to India, you get this shape. Mexico looks like this, and you might be able to recognize Italy from this boot shape country polygon. But if you want to really play it randomly, you can use the sample function again, but then it gets really hard because so many countries are just islands or really hard to detect by the shape or outline alone. It comes with the long and lat information, so maybe this can help you to put it on the map a little bit easier. Next I want to show you the geom count function. So the MPG dataset has a variety of cars with a city mileage and a highway mileage, and that's the correlation. But if you just use geom point, then you wouldn't notice that many of these values overlap. You could of course use geom jitter to introduce some noise, or work with a really low alpha value, and then you see where unique combinations of city and highway mileage lie, and that here you have an overlap of multiple responses. But the geom count function helps you in a sense that it provides information on the number of observations for a certain data point. So all of these are unique, but then increases to 2, 3 and up to 10 items with the same city and highway mileage. This geom count function can be helpful to get a better overview of your sample. For example, the diamonds data frame has over 50,000 diamonds with different cut and clarity values, and this is a quick way to visualize where most of your data falls. So you have often premium and ideal cuts, and the clarity is mostly VS1 and VS2 with some SI1, and sometimes you need to know that when you create models to see how big is your coverage in some of these more rare combinations of variables and whether they should be included in your analysis. Now, just to mention, there's something interesting with the grouping variable. If you set it to 1, then all of these dots in size add up to 100%, because the group is just the entirety of the combinations. So this proportion is 7.5% of your data, and then it adds up to 100%. But you can also choose cut for the grouping, and then these dots add up to 100% within each column. So now you see, even though that fair cut was really rare, in and of itself, it still adds up to 100% based on these clarity values. And so you see that the lowest clarity is not used to produce cuts of an ideal shape. This dot is really small. And if you set group to clarity, then the rows add up to 100%. So the best clarity is usually used for premium and ideal cuts. For the next two geoms, I produced some data frame based on the student's T distribution, producing 200 random values that can be accessed under the Y variable. And then if you plot it with the geom QQ, it will plot each value from your sample against the theoretical distribution. And with geom QQ line, you can add an orange line. And here you would be able to tell if there is some bias in your data that deviates from the distribution. Next is the very cool geom quantile function. So imagine that you plot from the MPG dataset cars with bigger engines, so higher displacement, and their highway mileage. As you would assume, bigger cars use more gasoline, so their mileage is reduced. If you add the geom quantile function, then it will introduce 3 lines to create the 4 quantiles, splitting the data proportionately into 4 equal parts. So now you could tell, based on which displacement, which cars fall into the top 25% of most fuel efficient and which in the lowest 25%. You can specifically set the quantile value, so if you just choose 0.5, you get the median. You can also create a sequence from 0.2 to 0.8 in steps of 0.2, which will split your data set into 5 equal proportions. And if you want to split it into thirds, you would choose 1/3 and 2/3 for quantiles, and then have this kind of split. Slowly coming to an end with the geom function or geom that can be used, for example, to show the theoretical distribution of the normal distribution. So here I just simulated 100 random values with a mean of 0 and a standard deviation of 1, and plot that on the x-axis in black. And then you can follow up with the geom function, where function is now the density of the normal distribution, and then you color it in red to see where these 100 points deviate. So just by random chance, they tended to be a bit bigger than expected, theoretically. This can also be used to just create an empty ggplot with the x-axis limitations of -5 to 5, and then follow up with the geom function to plot the normal distribution density plot. And you can also use this to investigate different features of your distributions. For example, the normal distribution, how does it look in shape versus the t-distribution with a degree of freedom of 1. T-distributions you often use with smaller sample size, where the variance towards the tails is higher, so more extreme cases can happen with a higher frequency. And the last function is geom_blank, where you can do all the mapping from your data to ggplot and follow it up with geom_blank, which will just create an empty chart, but it already has the x and y axis extreme points, so within this range your data will appear if you then add another geom like geom_point. However, this is not really different from just using the ggplot function without any geom. Thanks for watching this video. In the description below I will link to the cheat sheet where these geoms are ordered based on the type of data you have. I will also link to this online book about ggplot that will help you to get an even better understanding of the ggplot geomes. Until next time, here at the Data Digest. Bye bye.